by probing the quarks and gluons in the atom's nucleus with beams of electrons from a superconducting accelerator. CBAF has an educational mission as well. The CBAF Science Series features scientists and engineers who are gifted at making their work not only informative, but fun. The Science Series is held once a month during the school year in the CBAF Center Auditorium. The presentation is live, spontaneous, and for the most part, unrehearsed.
Good evening and welcome. Before we get started, we want to make sure you all know that.
Good evening. Welcome to tonight's Science Series program. I'm Beverly Hartline from CBAF, and it's my pleasure to introduce tonight's speaker, Dr. Christopher Chyba. Dr. Chyba grew up in Baltimore, Maryland, and attended college in Swarthmore, Pennsylvania at Swarthmore College. There he majored in physics, and while he was still a student, he wrote several scientific papers on such topics as black holes, recombinant DNA, and selling military supplies to China. After getting his bachelor's degree in physics, he went on to the University of Cambridge in England, where he got another bachelor's degree in mathematics and a master's of philosophy in philosophy of science and history. And then he returned to the United States, where he did a PhD degree with Carl Sagan, who I'm sure many of you have heard of, at Cornell, in the field of astronomy. Dr. Chyba is a planetary scientist who spent the last few years working for the United States government as a White House fellow, and now he's with the Office of Science and Technology Policy. I can give his disclaimer, which is that his views, the lawyers tell him he has to say that his views do not reflect the views of the United States government or the Office of Science and Technology Policy, but I think we'll find them very interesting and educational nonetheless. Please join me in welcoming him for his talk on collisions of comets and asteroids with the Earth. Dr. Chyba.
Thank you all for coming. I'd like to thank Beverly, except that she took my first joke line, so I'm not sure I should really thank her. And I'd like to thank CBAF for having me here this evening. I became a scientist because I thought that if I played my cards right, it offered the best chance to explore, the best chance to have some adventure, and the best chance to give me a better understanding of where I came from and how I fit into the world. And you can judge for yourself from the talk tonight whether science is a way of getting at those kinds of questions. If we could have the first slide and the lights down. This July, comet Shoemaker-Levy 9 hit Jupiter. This is a remarkable event. It's unlikely to happen again in our lifetime or the lifetime of our grandchildren. Shoemaker-Levy 9 was a comet, we think, that passed very close to Jupiter a couple of years ago, so close that Jupiter's gravity ripped it apart into about 20 different pieces. It also pulled it into an orbit around Jupiter, which led it to collide with that planet, shown here in this sort of artist drawing. And maybe we could have the lights down a little bit more. This is actually a composite photo of the comet approaching the planet. There are a number of reasons why you might want to spend time studying the impacts of this comet with Jupiter. The first is just what a unique event it is. The second, though, is that if you can learn something about what happens when something like Shoemaker-Levy hits the planet Jupiter, it'll tell you things about what happens when asteroids and comets hit the Earth, which is directly relevant to our lives in a whole set of ways. And that's what I want to talk mostly about this evening. But because we had this remarkable spectacle this summer, I'll spend just a few minutes talking about Shoemaker-Levy 9. This is an infrared photograph taken in Australia of one of the impacts, the impact of the so-called G fragment with Jupiter. At the time of the impact, the brightness from the collision was brighter. The collision itself was brighter than all the light coming from the planet. This explosion is probably about 10 million megatons in energy. What does that number mean? The biggest warheads, the biggest nuclear warheads that are commonly employed in the arsenals of the United States or the former Soviet Union on Earth are about 10 megatons. So this explosion is about 1 million times bigger in energy than the biggest nuclear explosions we were able to make on Earth, or at least that we desire to make on Earth. And this is what happens in one of these impacts. This is a space telescope photo. And what you're seeing here is a sequence of images over about a time period of about 12 minutes. Here's Jupiter before the impact. The comets hit, and when it hits, it causes an enormous plume of gas and dust that rises up above the planet. And here you see the plume rising over this period of 12 minutes. It rises to a few thousand miles up, it flattens out, and because of Jupiter's gravity, it falls back down. A lot of these plumes left dark splotches on Jupiter that scientists are still tracking with telescopes to see what the long-term evolution of those impacts, of those splotches is. Doing science in the kind of media environment that the scientists had to work in under Shoemaker-Levy 9 is no joke. You're swamped with the press. You don't have time to think. You're sleep deprived because you know the press is only going to pay attention for about the week that the impacts are happening. So I like to show this photo to give a sense of what doing science under those conditions is like. There's one scientist in this picture. Your job is to find her. Well, this is Anne Verbischer. At the time this photo was taken, was a graduate student at Cornell. And this is the media feeding frenzy. One of the things this tells you is that you really shouldn't believe any result that comes out the week of an event like this. First of all, the scientists haven't slept in 2 days. Secondly, they have to do their analysis in 0 time. It's not the way you usually do science. There are a lot of ideas thrown out that later will have to be withdrawn because there just isn't time to do it right. Shoemaker-Levy 9 hit Jupiter, comets and asteroids hit Earth. This is the Barringer crater in Arizona. It's a little over 1 kilometer in diameter. If you're driving across Arizona, it's only a few miles away from the main east-west highway. Well worth a visit. You need to hit Earth with an object with an energy of about 15 megatons to excavate a crater of this size. 15 megatons, again, is the energy of about the largest warheads in the U.S. or former Soviet, Russian arsenals. You would like to know how often this sort of thing happens. You sure wouldn't want to be nearby when this happens. You'd like to know how often it happens, how much you have to worry about it. So we're going to step back a little bit. This is a small impact. This is a comparatively small impact. We're going to step back to a bigger one. Before I talk about the bigger one, though, I'll mention that we know a little bit about what causes these craters, what actually hits the Earth to cause one of these impacts. There's a meteorite. There's a chunk of a meteorite called Murchison, a so-called carbonaceous chondrite, a very carbon-rich meteorite. So we have direct samples from the meteorites of what the stuff is that hits the Earth. What's hitting the Earth are asteroids and comets, or small pieces of asteroids and comets. Murchison is a small piece of a so-called carbonaceous asteroid. Carbonaceous meteorites come from carbonaceous asteroids. So we already have samples of these big objects.
How big is that?
Oh, that object you just looked at is about 8 inches across. This object is about 8 miles across. This is Gaspra, an asteroid. This picture was taken by the Galileo spacecraft en route to Jupiter. Its trajectory was designed to pass by a couple asteroids so we could take images of them close up. This is an example of the kind of body that the meteorites that fall to Earth came from. The other kind of body that hits the planets are comets. This is a picture of Halley's Comet, a few years old. Comets are about 50% water ice, unlike asteroids, which are mostly rock or iron. Comets have a lot of water, so that when they get near the sun, the heat from the sun evaporates the water. The water comes off and is swept back out from the sun. And that's the origin of this cometary tail and this bright coma, the head of the comet. That's all water and some dust reflecting sunlight. So those are the two classes of objects we're talking about, the two types of objects that are going to hit the Earth, comets and asteroids. I showed you Barringer crater, which hit the Earth maybe 30,000 years ago. We're going to go a lot farther back with this photo. We're going back to 65 million years ago, the time of the extinction of the dinosaurs. What you see in this picture is a thin layer. This coin is about the size of a quarter. This is a layer of clay that's very rich in the element iridium. Iridium is extremely rare on the Earth. It's in a class of metals that include gold and platinum, and that's why those metals are so valuable, because like iridium, they are extremely rare. But it's very common in asteroids. We know that directly because we have pieces of asteroids, the meteorites. This is these are rock strata, so this is a section through time. These are older rocks, these are younger rocks. This is the age of the dinosaurs down here. Then there's this clay layer full of iridium, And then this is the so-called tertiary period, the age of mammals. All over the Earth, you find this clay layer rich in iridium. When this layer was found in the late 70s, the idea was suggested that it was the residue of a large asteroid or comet that hit the Earth 65 million years ago and deposited. It would hit the Earth, it would throw all this dust up in the air. It itself is iridium rich. The iridium would fall out of the atmosphere and create a layer, an iridium-rich layer all over the surface of the Earth. And if you know how much iridium is in asteroids, which we do from the meteorites, you can figure out how big that object had to be, and it had to be about 6 miles across. So this was indirect evidence that something big hit the Earth 65 million years ago. And the question, the immediate question, of course, was it just coincidental that the dinosaurs went extinct at exactly the time this big asteroid slammed into the Earth? Well, this is the smoking gun for that impact. This is the crater that impact left. It's called the Chicxulub crater. It's under Yucatan, Mexico. This is a false color image. It's based on gravity data. But this is the crater now filled in, but this is the crater left behind, and this is about 120 miles across here. It's a big crater consistent with an object about 6 miles across hitting the Earth and depositing that clay layer. So there's no question anymore that the Earth was smacked by something very big 65 million years ago. This is a kind of pterodactyl's eye view of that collision. A 6-mile asteroid coming into the ocean, and it's bad news for these guys. It's bad news for a lot of reasons. The first reason that was suggested, which is probably still the most important, is that such an explosion that's that big, will cause a globe-encircling dust cloud to be thrown up into the air. The Earth will be, and so the atmosphere of the Earth will be full of dust. That dust will block out the sun, perhaps for as much as a half a year or a year. So everything crashes. Plants can't photosynthesize anymore because they can't get the sunlight. The food chain collapses. The dinosaurs all die out. And here's the Triceratops going to the dinosaur graveyard. But perhaps small animals that are scavengers, like these little mammals down here, our ancestors, can make it through that kind of event. And there are a lot of other things that happen, not just this nuclear winter type of scenario, this collapse of the food chain. There are a lot of other things that happen. The Yucatan Peninsula is rich in carbonate rocks, rich in carbon dioxide. It looks like after you get through this global winter, because of all the dust, you've vaporized so much carbonate rock, put so much carbon dioxide into the atmosphere, that you then have global warming that lasts for thousands of years. So if the freezing doesn't get you, the global warming does, and the result is a mass extinction. Some types of animals make it through, though. So the history of life on Earth, if this picture's right, is intimately bound up with the impact history of the Earth. Big impacts on Earth have the most dramatic effects imaginable for the history of terrestrial life. One other remarkable thing about what's found at the Cretaceous-Tertiary boundary, that clay layer, in the jargon of the field it's called the KT boundary. There are extraterrestrial amino acids found at that layer. Amino acids are the building blocks of the proteins in our body. They are the standard sort of building blocks you need if you're worrying about how to get the origin of life going on our planet. And it looks as though the impact 65 million years ago deposited or created in the explosion amino acids, which we can now detect at that layer. And you don't find these anywhere else. You only find them at that layer. So there is a mechanism to deliver the sort of organic molecule building blocks or to generate them in the explosion in these big impacts. That in turn may relate to the origins of life on Earth. To get the origins of life on Earth rolling, you need to have the building blocks in place. You can either make them here or you can bring them in from outside. The Cretaceous-Tertiary boundary results may be pointing us towards a mechanism for bringing the building blocks in. We'll say more about that later in the talk. In fact, let's go all the way back to the beginning now. Look at the top half of this slide. This is a fossil. It's a 3.5 billion year old fossil from rocks in Western Australia. It's a fossil bacterium. Looks like I should be more careful, a fossil blue-green algae, perhaps 1/10 of a millimeter long. And again, this is from a suite of rocks that are about 3.5 billion years old. I remind you, the Earth is about 4.5 billion years old. So about 1 billion years after the formation of the Earth, there were these rather sophisticated, single cell, but probably photosynthesizing, because these look a heck of a lot like blue-green algae do today, very sophisticated photosynthesizing microorganisms on the Earth 3.5 billion years ago. This is another fossil. This is a fossil stromatolite, and the fossil is this dome-shaped section right here with these layers or laminae. What's a stromatolite? Stromatolites exist today. This rock's 3.5 billion years old, but stromatolites exist today. These are stromatolites in Sharks Bay, Australia. These are a little bit bigger than the ones we just saw. These guys are maybe a meter across. The one you were just looking at was maybe 5 or 6 centimeters. In fact, you can see, let me go back to it for a moment. You can see this slide in the Natural History Museum at the Smithsonian in Washington. It's on the first floor. I strongly recommend it to you. You're looking at one of the oldest organisms on Earth, at least that we have a fossil from, when you're looking at that fossil. These are stromatolites today in Australia. What's a stromatolite? This is what happens with a stromatolite. Stromatolites are made by algal mats. You have algae in a mat, and the algae trap sediments, and they put down a new layer. They're living in what's called an intertidal zone, so the tide's washing in and then it's washing out. And they're trapping sediments each time the tide washes in. The sediments get left behind when it goes back out. So you build up these layers. And because they're trying to take these are photosynthesizing organisms, they're trying to take the shortest route to the sun. See, they trap these sediments that get partially buried. They have to work their way back up through those sediments to get to the sunlight. They wind up forming these dome-shaped layered structures, stromatolites. And we have fossils of these stromatolites that are 3.5 billion years old. Early in the history of the planet, there was photosynthesizing life. Now that's a problem. And it's a problem that's illustrated by this slide. This slide shows the ages of different parts of the Earth. The ocean floor is all very young. The ocean floor is typically less than 100 million years old. I know that seems like a long time, but in the history of the planet, 4.5 billion years old, it's short. The terrains denoted in black here are the oldest terrains on the planet. They're so-called Archean terrains. They're 2.5 billion. They're older than 2.5 billion years old. But the really old rocks on the Earth are in only 3 places. Western Australia, and we just saw some fossils from there, South Africa, and the southern tip of Greenland, the so-called Ishua Formation. These rocks are 3.5 billion years old. These rocks are 3.8 billion years old. These are all sedimentary rocks, so they're the result of sediments being laid down, and you can preserve fossils in those kinds of rocks. But especially the ones in Greenland have been reworked a lot. It's very hard to find fossils in them. Nevertheless, in every one of these suites of rocks, there are either fossils of life or there are other more subtle indications of life having existed at that time. You see the problem. The Earth's 4.5 billion years old. The oldest rock record we have on Earth is 3.8 billion years old. There's no record left of the first 700 million years of the planet's history, which means you can't learn anything about the first 700 million years of our history, almost the first billion years of our planet. You can't learn anything about it from geology. There's no record left. The Earth is too active a planet. There's plate tectonics, crust gets pulled down and melted, there's erosion from rain. We just don't have any of the original surface of the planet left. Nevertheless, in the oldest samples we do have, there's life. There's fossils of life. So if you want to understand what the heck happened during the origins of life, these rock records can't do it for you. There's no record left on Earth that's old enough to tell you what the environment of the Earth was like at the time of the origins of life. What that means is if you want to learn about the Earth's environment at the time of the origins of life, you have to leave the Earth. You have to go to the moon and the planets. And that's not just metaphorically true, it's literally true, and that's what I want to describe right now. So let's go. This is the moon. It's a better picture than one you could take in your backyard, but it should be pretty familiar. And if you go out in the night and have a look at the moon, you should notice a couple things right away. Mainly that it's divided into these bright and these dark spots. And if you look at it carefully, you can convince yourself the dark spots all tend to be circular. What's the scale? This is the Mare Imbrium. This is about 1,200 kilometers across, so about 600-700 miles across. The reason these guys are circular is because they're giant craters that were excavated on the moon, typically more than 3.5 billion years ago, exactly as old or older than those fossils we were just looking at. And they have since filled in with dark black lava. Lava that looks a whole lot like this stuff. This is a lava flow of Kilauea caldera in Hawaii, and it's the same sort of stuff. It's dark and it's black. This is a close-up of that flow, and this is exactly why the dark parts of the moon look dark. It's made out of this dark lava that's filled in these big craters. So that's what you're seeing when you're looking at the moon at night and seeing the dark spots that look like circles. You're looking at giant craters that were excavated on the moon when the Earth was still in its infancy. How do we know that? We know that because we've gone there. We've gone there and we've brought pieces back. Now, remembering that nothing that I say necessarily reflects the views of the U.S. government or the White House Office of Science and Technology Policy, we did not go to the moon for scientific reasons. We went to the moon because of the Cold War. Nevertheless, we learned an enormous amount about the history of our solar system by going to the moon and the history of the Earth indirectly. We went there and we brought pieces back. This is a spacecraft, the lunar module on its way back. What did we do? This is the Apollo 12 landing site. Apollos 11 through 17 went to the moon. 13 had a serious accident on the way. All the others made it. The arrow shows exactly where it landed. This crater here is called Surveyor Crater. This sketch map shows what the astronauts did when they got there. This is before the lunar buggy, the lunar rover, was invented, so they had to walk everywhere they went. Here's a scale. This is 100 meters. The scale here is 100 meters. So these traverses that the astronauts did, shown by the lines, are on the order of hundreds of meters, hundreds of yards each traverse. They couldn't go very far. This is Surveyor Crater. Let me just step to the side a moment to mention something remarkable about Apollo 12. They went to Surveyor Crater, and in fact it's called Surveyor Crater because the Surveyor spacecraft had landed there about 2.5 years before. And it's a tribute to how good the navigation was on only the second Apollo mission that they could land within a couple of football fields of where this previous spacecraft had put down 2 years earlier. And they went to it, and they brought some pieces back, and you can see why you might want to do that. If you bring pieces of Surveyor back, you have material that sat on the lunar surface for 2.5 years, so you know exactly when it got there, and it'll tell you immediately about the radiation environment, about the micrometeorite environment, a whole lot of information you can get by bringing some pieces back. Here are the astronauts detaching the Surveyor camera from the spacecraft. That camera was brought back to Earth. It was given to a lot of people, but amongst other people, it was given to exobiologists who found freeze-dried bacteria inside. Bacteria that were still viable. When they were put in culture, they were able to reproduce. These were not moon bugs. The spacecraft was supposed to have been sterilized before it was sent. It was imperfectly sterilized, and some streptococcus, strep throat bacteria, were left in the camera. Think about what that means. These bugs survived 2.5 years of hard vacuum and hard radiation. They freeze-dried, but they were still viable when they were brought back to Earth, a kind of reminder about how hardy some simple types of microorganisms are. Getting back to our main point, besides pieces of the Surveyor spacecraft, you picked up a lot of rocks, and you brought the rocks back to Earth. This is the liftoff from the surface of the moon, returning those rocks. So what can you do? This is one of the few technical slides I'll show this evening, and in fact, let me get rid of it for a moment. We'll spend a little bit of time with it, but all you need to do is follow the gist of the argument. What have you done? You're bringing rocks back. You can date the rocks using standard radioactive dating techniques. You know how old the rocks are. You've landed on some sort of lava flow on the moon that's covered with craters. You date the rocks in the lava flow, you learn how old that lava flow is. You know when that surface was formed. All the craters that were formed on that surface were formed subsequently to the solidification of that lava. Otherwise, you wouldn't see them. It would be like dropping rocks into the ocean. The craters would disappear. So you can count the craters on that surface, and you know how many craters formed on the moon since that lava flow solidified, which you've dated using radioactive dating techniques. And that lets you make this kind of diagram if you go to lots of different spots on the moon. On the y-axis here, this is just a measure of the number of craters. You don't have to worry about the details of the measure, but it measures how many craters there are on the surface of the moon per square mile or whatever units you're using. And notice that every big division you go up by a factor of 10. On the x-axis here is the age of the surface. So this is 4.5 billion years ago when the moon formed. This is today. You land on all these different spots on the moon, you count craters, and you date the rocks, and you can make a plot of how many craters formed on the moon as a function of time. And if you do that, you discover that over the last 3.5 billion years, the data aren't great, but you can infer a lot from them. Over the last 3.5 billion years, cratering's been pretty low. Prior to that time, in the first billion years of the moon's history, cratering was exponentially higher than it is today. Exponentially higher. So the moon was really being slammed often in its first billion years. And you know how much more often than it's being slammed today because you have these data points. If you know how much stuff was hitting the moon, you know how much stuff was hitting the Earth. You know how much bigger the Earth is. You know how much more gravity the Earth has. So you can calculate, it's a kind of statistical calculation, but you can calculate how much more stuff had to hit the Earth, given what you know about how much stuff hit the moon. And about 25 more times stuff hit the Earth as hit the moon. So the Earth collected 25 times more asteroids and comets in its first billion years of its history than the moon did. Well, that's interesting for a whole lot of reasons. One reason it's interesting is that it means the Earth got hit by something the size of Halley's Comet about 10,000 times early in its history. This is a picture of Halley's Comet from the Giotto spacecraft, the European spacecraft that made the closest approach to Halley's in '86. And the scale here is about 6 miles from end to end. The sun's up here. The comet is evaporating. Its ice, which is exposed to the sunlight, is evaporating, which is why it's bright on this side. These are jets of ice and dust jetting off towards the sun, being driven by the heating from the sun. Halley's Comet is the same size object as hit the Earth 65 million years ago, and we think probably caused the extinction of the dinosaurs. So early in the Earth's history, the Earth experienced that kind of event something like 10,000 times. Earth was not a pleasant place to be in its first billion years. And in particular, if you were trying to get life started, it's an extremely hostile environment to try to get the evolution of life started in. A very different picture from the picture we had only, say, 20 or 30 years ago, which was a kind of gentle, calm environment, warm, friendly. Not friendly at all, very hostile, impact-ridden, big impacts regularly. There's another interesting lesson from this. This is a painting by Frederick Church. This is in the Dallas Museum of Art. If you know how much stuff hit the Earth, because you know how much stuff hit the moon, you count the craters on the moon, you can go from the craters on the moon to the mass, the size, the mass of the objects that hit the moon to excavate those craters. Do you know how much matter, how much material the moon swept up in its first billion years of history? Then you can go, using that factor of 25 I mentioned, to figure out how much stuff the Earth swept up in its first billion years of history. That was caused by comets and asteroids. Comets are about 50% water. So one question that comes to mind is, if a lot of the craters on the moon were caused by comets, and comets are 50% water, how much water did the Earth collect from comets in its first billion years? If you take that seriously and play with it, it turns out the Earth collected just about an ocean's worth of water in its first billion years. It also collected, because we know the composition of comets now, so we can do this calculation. We know because we had spacecraft go through Halley's. It collected about the same amount of carbon as exists on the surface of the Earth. You can play this game for a lot of elements, and there's a consistent picture that's built up, which is that what people call the biogenic elements, the elements that you really need for life, the critical elements for life, carbon, nitrogen, compounds like water, probably have their origin in this bombardment that took place late. It looks as though the Earth formed in a pretty high temperature part of the solar system and formed devoid of elements like carbon, nitrogen, compounds such as water. And those compounds came in as a kind of late accreting veneer, a veneer of material that was sprinkled over the surface of the Earth during its first billion years due to the impacts of comets and asteroids. So there's a direct connection, if this picture is right, between the possibility of life on Earth and the kind of elements you bring in the cometary and asteroidal bombardment. If you hadn't had that bombardment, it would have been a whole lot harder, if not impossible, to get life rolling because the basic materials you need for life would not have been here. It's even possible that the kinds of compounds you needed for life, amino acids, have their origins in those impacts. What I've just described is, in effect, the way in which impacts help the origin of life on Earth 3.5 billion, 4 billion years ago. There's another side to this, though, which I've already mentioned, which is how violent the early Earth's environment would have been. To get a sense of how violent it is, let's just look at this picture. This is the Orientale Basin on the Moon. This is maybe 500 miles across. If it's on the Moon, probably something like 25 objects big enough to excavate this kind of crater hit the early Earth. How many of these big craters are there on the Moon? This is a sketch map for the Moon. I mentioned before that Imbrium, it's about 1,200 kilometers, or about 700 miles across. This is the South Pole Aitken Basin. That's 2,500 kilometers across. We're sure of its existence now because the Galileo spacecraft photographed it, and we're dead sure that basin exists. It's a 2,500 kilometer crater. That's a 1,200-mile crater on the Moon. You have to hit the Moon with something very big to excavate that kind of crater. And if these objects were hitting the Moon, they were also hitting the Earth. What are the consequences for those kinds of impacts on the Earth for the history of the early Earth? Well, the most dramatic consequence is that the biggest impacts on early Earth would have been bad enough to raise the temperature of the entire surface of the Earth to several thousand degrees for a period that would have lasted a few months. So you would have, over the entire surface of the Earth, you would have created an oven, in effect. How do you do that? In a big impact, you vaporize so much rock that you actually create a globe-encircling rock vapor atmosphere that lasts for a few months. And that's what's shown on this sketch map here. The atmosphere of the Earth becomes rock vapor for a period of a few months. So for a few months, you're breathing rock vapor. And that's bad. That's real bad. It's bad if you're trying to evolve. It's bad no matter what you're trying to do. And the rock vapor evaporates the oceans. And it puts the entire ocean into the atmosphere as a hot steam atmosphere. So then you have a few more thousand years where you have an enormous greenhouse atmosphere which keeps the temperature of the surface of the Earth to about 1,000 degrees. Eventually, things cool down, the oceans rain back out. And if you believe the lunar cratering record, this happened probably half a dozen times in the early history of the Earth. This is probably a planet sterilizing event. It's probable that half a dozen times in the first billion years of Earth history, you sterilized the surface of the planet. So even if you had gotten life rolling in its first billion years, you exterminated it. We're the happy products of the fact that that one more impact didn't happen. Let's step out a little bit. Let's go out a little farther in the solar system now. This is Mars. Mars is an interesting world for a number of reasons. One is that the southern hemisphere of Mars is very ancient, heavily cratered. The northern hemisphere is much younger, lots of lava flows, recent lava flows in the northern hemisphere. There are a lot of similarities, which I won't go into detail on, between the cratering record in the southern hemisphere of Mars and the Moon, enough to convince people that the same set of objects that cratered the Moon cratered Mars, incidentally cratered Mercury as well, and therefore would also have been cratering the Earth, even though there's no record on the early Earth left from that time. This is another view of Mars that makes it seem a bit more Earth-like than the last photo did. These are volcanoes. These are clouds, first of all. The white splotches here are carbon dioxide clouds on Mars. These are volcanoes. This is the Valles Marineris, which is the width of the United States. It's a huge valley in the Martian equatorial region. We've been to Mars. This is a picture taken in 1976 from the Viking lander. The Vikings went to Mars to search for life there. They didn't find any, and in fact, they found a very hostile surface that's probably deadly to most life as we know it. But Viking found some other things. Even if there's not life on Mars today, it looks as though early Mars was much more Earth-like than Mars is now. This is a mosaic of Viking photographs that shows a river. Not a river that's still flowing with water, but a riverbed on Mars. This is just a blow-up. You can date roughly, very roughly, you can date the ages of these rivers, these so-called valley networks, to use the technical jargon, on Mars by counting craters. Surfaces that have more craters are older. You can try to use the Moon and the cratering record on the Moon, which we've dated, to get some sense of the ages. It looks as though 3.5 billion years ago on Mars, there was flowing water on the surface. that excavated these rivers. In fact, there are lakes that you can identify. There are about 30 small lakes, small meaning the size of the Great Lakes, that people have now mapped on the Martian surface that also appear to be about 3.5 billion years old. So at the time of the origins of life on Earth, Mars had liquid water. Presumably it was much warmer than it is now. Mars now is a kind of frozen desert. But at the time of the origins of life on Earth, Mars was much more hospitable. And you have to ask, if Mars had liquid water, if it was warm, at the same time that life got rolling on Earth, would there have been life on Mars, even if the planet's a freeze-dried, sterile desert now? If that were the case, would there be a way to look for fossils on Mars? We looked at some microscopic fossils from the Earth before. Are there sites on Mars where you'd want to go to look for fossil life on Mars? How do you even think about that question? How do you even approach it? If they're fossils, you might hope that they've been preserved in the Martian permafrost. Most of the surface of Mars is covered, it's frozen ground at about minus 70 centigrade. It's permafrost. Is there any hope for finding fossil life there? I'm going to get back to that question in a moment, but I want to have one other sidebar here, one other diversion, which is to talk about something called the face on Mars. A lot of you have probably seen a picture of the so-called face on Mars. It tends to show up a lot in the National Examiner or Enquirer and newspaper and supermarket tabloids. There are two views of the face on Mars. There are two ways you can look at it. There are two possible explanations. One is that if you photograph tens of thousands of piles of rocks on Mars, sooner or later you'll find one that kind of looks like a human face, especially if you choose your lighting angle just right. Another possible explanation is that it's the remnant of an ancient race of super intelligent beings on Mars, and they built this as a kind of signal to us when we eventually got smart enough to build spacecraft that would go to Mars and we could see it. Well, this is a crater. This is a different object on Mars. This crater right here in what's called the Argyre Planitia. And this is the happy face on Mars. The smile and two eyes. And there are two possible explanations for this feature. One is that if you photograph tens and tens of thousands of craters on Mars, sooner or later you'll find one that has a few rocks in it in just the right way to look like a happy face. The other explanation, though, is that there was a race of ancient Martians who left this as a sign to us that all of them were very happy. My sister has a photograph of a pile of rocks in the Grand Canyon. It looks a lot like a giant duck. Now, there are two possible explanations for that pile of rocks in the Grand Canyon. But I think I've made my point. Let's get back to the subject at hand, which is permafrost on Mars. Was there life on Mars? How do you find out about that now? Well, we're not bringing back any pieces of Mars anytime soon. We're not going to be affording that for a long time. But one way to try to get at that question is to go to places on Earth that are the most Mars-like places you can find on the Earth. Where are those places? Well, one place is northeastern Siberia. This is a picture out of a cargo plane taken in 1991, a few months before the coup in then Soviet Union, flying over northeastern Siberia. And we went there because some of the oldest permafrost on the Earth is in northeastern Siberia. This is the Arctic Ocean here. In fact, this is actually the ice pack up here. And this is, we're well north of the tree line. Trees can't grow this far north, but scrub that's this high can grow. You notice these sort of polygonal features here. These are standard permafrost features. You see these same features on Mars, by the way, except they're much bigger. The lower gravity on Mars lets those kind of features grow to much larger scales. This is us putting in, this is Ed Burrell, a member of the U.S. expedition. This is camp. Dinner was always something to look forward to. And you can tell by this next slide how much we're all really enjoying it. I want to say just a few words. Firstly, I just want to mention that it's very difficult to do science under these conditions. This is Mary Allen at the time, who Mary was a microbiologist at the University of Florida, grad student in microbiology. Every speck you see in this photograph is a mosquito. This is one that's very close to the lens of my camera. So you can see that Mary's wearing mosquito protection. Her hands are slathered with DEET. It's no joke trying to do any kind of science under these conditions. One of the things we were doing in the field was drilling down about 100 feet to where you got to 3-million-year-old permafrost, because the Soviets had reported that they had recovered 3-million-year-old bacteria that had been frozen in that permafrost during the intervening 3 million years that were still viable when you put them in culture. That's interesting in and of itself, of course, but it's also interesting as an analog to Mars. The permafrost here is about minus 10 degrees Celsius. If bacteria can survive at minus 10 for 3 million years, could something like bacteria survive at minus 70, the temperature of Martian permafrost, for 3.5 billion years, 1,000 times longer? You can't really answer that question by going to Siberia, but you can start to get a handle on it. So that's why we went. Incidentally, it looks like it's for real, like those bugs really have been down there for 3 million years, frozen in the permafrost. So this is science in the tundra. Again, notice the mosquito netting protection. No joke, it's very difficult to operate under these kind of conditions. We're in Siberia. Let's just say a few final words about other things that have happened in Siberia. What I just described was going to Siberia because of the analogy to Mars. There's at least one other place in central Siberia where you might want to go to learn something about the impact environment of the Earth, to learn something about what happens when small asteroids and comets hit the Earth. And that's to a place called Tunguska. In 1908, right here, over the Tunguska River Basin, there was a 15 megaton explosion about 6 miles up. Again, 15 megatons is the size of the biggest warheads in our arsenals. But this is 1908, 40 years, 35 years before the invention of nuclear power. What happened? That's always been the mystery of Tunguska. And there have been a variety of more or less exotic explanations proposed. It looks as though a small asteroid exploded in the atmosphere. This is the Tunguska River Basin, which flows into the Yenisei River, one of the 3 great rivers of Siberia. And this man is the first scientist who got to the site. This is Leonid Kulik, who got there about 20 years after the event. The only witnesses to the event were Tungus reindeer herdsmen who saw it, but word didn't get out to the outside world for 15 years. Kulik managed to outfit an expedition to go to Tunguska to try to see what had happened. He was expecting to find a crater there. He found no crater, and that's really the origin of the mystery. Kulik, incidentally, died during the Second World War in the defense of Moscow. This is Ilya Potapovich, who was a Tungus reindeer herdsman who was a guide for Kulik in his first expeditions. Again, no joke. They actually wintered over at the site one year. This is a baggage train providing them with supplies in the winter. During the spring, you've got to push your supplies up these streams. Notice again the mosquito protection. This is mosquito hell that they're in. This is the famous picture of Tunguska, the toppled trees, the trees broken and knocked over like matchsticks. This is what Kulik was seeing for the first time as he wandered into the site with his Tungus guides, searching for what had happened and where it had happened. There's another picture showing a tree that's just been uprooted and knocked over. And you can actually measure, and the Russians, the Soviets at the time did measure, something like 10,000 different trees in the directions they had fallen in, presumably with the help of a lot of students. And they made this sort of map. The arrows here show the direction of the tree fall. And what you see is that the trees are blown outward from a central point. And that's where they figured the impact had occurred. They went there expecting to find something like the Barringer Crater, Meteor Crater, Arizona. In fact, Kulik knew about Meteor Crater. That's exactly what he expected to find at that impact site. How big is this site? This is what we were just looking at. It's something like 800 square miles, 2,200 square kilometers. And this puts it in context compared to the city of New York or the city of Washington, D.C. Incidentally, this is the kind of map you make if you're hoping to get funding from Congress to investigate how much you have to worry about these kinds of impacts. It's especially important to compare it to Washington. But nevertheless, it's clear that it would be very bad for something like this to happen over top of a major metropolitan area. This work relies a lot on what we know about the effects of nuclear weapons. It takes about the same amount of overpressure at the surface of the Earth to topple a tree as it takes to explode a frame house. Okay, so everywhere where the trees got toppled, suburban houses would be exploded. Clearly, it would be very bad news for this to happen over an inhabited area. On the other hand, the question is, how often does this sort of thing happen? To understand that, you have to understand, to answer that, you have to understand what the heck did happen. This is ground zero. The trees are still, this is Kulik and some of his sled dogs at ground zero. The trees are still standing at ground zero. They've been stripped of their branches and they've been charred, but they haven't been blown over. We understand that as well, again, through another grim analogy. This is ground zero at Hiroshima, scene of the first atomic blast. The trees are still standing. That's understandable if you picture the explosion taking place in the atmosphere. So the trees that are directly below the explosion, the shock wave comes down. It doesn't knock them over. It strips the branches off them, but the shock wave's going straight down. It doesn't topple them. Farther away from the center, though, the shock wave's coming out, and it's going to knock your trees over. Without going into a lot of the details, we now understand the Tunguska event very well. We understand it as due to a small asteroid, about half the size of a football field, exploding in the atmosphere, which we now understand to be a typical fate for small asteroids in the Earth's atmosphere, about 6 miles up. We've done the analytical modeling to figure out why that happens and how often it should happen. And rather than dwell on the details of why it happens that these guys blow up in the atmosphere, I'd like to spend the last few minutes talking about how often it happens and how much we need to worry about it. So that'll be it for the slides. And let me talk a bit about how much we have to worry about this sort of thing. Congress asked NASA to try to answer that question. Not only to answer the question of how much we have to worry about Tunguska-like events, but how much do we have to worry about the next Shoemaker-Levy 9? How often will something like Shoemaker-Levy 9 hit the Earth instead of Jupiter? How often does something like the extinction of the dinosaurs occur? Do we need to worry about this? And NASA's answer was a report called the Space Guard Survey that was delivered to the Congressional Science Committee, Brown's Committee. And these are just a few of the findings of that report. Let me describe them briefly. The first thing you want to know is how many of these guys are out there. How many asteroids and comets are currently crossing the orbit of the Earth? Every now and then one of them hits us. How many of them are out there whizzing by? The labels on the axes here aren't important. Really, the line and the labels right on the line tell you everything you need to know. Let's start here. These are 1 kilometer size asteroids that are in what are called Earth-crossing orbits. These are asteroids whose orbit crosses the orbit of the Earth, so they can potentially hit us. They're not necessarily going to hit us, and in fact, typically they'll miss us by a wide margin. But eventually, if you wait long enough, the Earth and the asteroid will be in just the wrong place at the wrong time, or the right place at the right time, depending on how you look at it, and we'll get smacked. There are about 2,000 1-kilometer size asteroids. That's about half a mile across, whizzing by the Earth. How do we know that number? We know that number because we've looked for them with telescopes. There are about 4 telescopes on the planet Earth that are currently scanning the skies looking for asteroids. It's a very low-level effort. These are all underpaid astronomers doing this work. In fact, the total number of people trying to catalog the asteroids that cross the Earth's orbit is smaller than the size of the staff of one McDonald's restaurant. One can wonder whether that's an appropriate use of our resources. We've looked at enough of the sky. We've actually identified about 200 of these objects of this size. We think we've looked at about 10% of the sky so far. So we think that there are about 2,000 of these objects out there crossing the orbit of the Earth. The number of objects at smaller sizes gets quite phenomenal. These are 100-meter objects. Tunguska is about half that size. There are probably 1 million objects the size of Tunguska crossing the orbit of the Earth. But the question is not just how many of them are out there crossing our orbit, but how often do they actually hit us? The likelihood of any one of them hitting us is very, very small. But we understand that well enough to go a long way towards answering that question. And that's this plot, which I think will be my last slide for the evening. So this is kind of the punchline. How often does this stuff happen? And then once you know that, you can start wondering, you start asking how much should we worry about it and what should we do about it. So on the y-axis here is time. How often events occur. Every year, once every 1,000 years, every million years. And on the x-axis is energy. Tunguska came in at about 15 megatons. The event that ended the age of the dinosaurs was about a 100 million megaton event. That's not even on this scale. That's off scale over here somewhere. So here's Tunguska. And we know now from these statistics, from these observations, that something like Tunguska happens once every 300 years or so. Remember, 3/4 of the surface of the Earth is water, so 3/4 of the time that explosion happens over the ocean, probably doesn't hurt anybody. So only once every 1,000 years does it happen over land, and usually then it's going to happen over the vast stretches of the land where there's not much population. You probably don't have to worry about events like Tunguska. They're very unlikely. On the other hand, there are in fact several times a year 20 kiloton explosions in the atmosphere, high in the atmosphere. Those are explosions as big as the explosions that destroyed Hiroshima and Nagasaki. But they occur high enough that we don't even feel the shock waves from those explosions. That number is now confirmed from declassified satellite data. The Department of Defense watches the atmosphere for nuclear explosions, and they see these explosions as well, and they see several a year. That's a good number. And then you can ask, what happens down here? What happens if you get hit by something pretty big, something the order, say, of a half a mile across? Well, first of all, that only happens once every million years or so that doesn't happen very often. But secondly, it is a disaster when it does happen. It's not as big a disaster as the event 65 million years ago that exterminated the dinosaurs. But if we get hit by an object that's about half a mile across, that object would probably raise enough dust into the high atmosphere of the Earth that the sunlight would be effectively blocked for a few months, for a growing season. It's quite possible that global agriculture would collapse for one growing season. That's not going to affect us too much. We have a lot of canned food. We would make it through, but the vast majority of the Earth depends on the harvests. So while the first world might make it through that kind of disaster, much of the third world might well starve. You have here, short of nuclear war, you have here, I think, the most extreme example of a very rare event that carries with it extremely dire consequences. And as a society, I don't think we're good at evaluating, at knowing how to deal with those kinds of events. It almost never happens, but if it does happen, it's really, really bad. What should we do about it? Well, again, remembering that I'm speaking in no official capacity, I would say what we should do about it is find out where the Earth crossers are. We know where about 10% of them are. Let's catalog them. Let's find out where 99% of them are. And then we'll know. It won't be a statistical problem anymore. We'll know at that point whether we're going to get smacked anytime soon. You can do that kind of survey for several $1 million a year. It'll take about 10 years. And then, the society has to judge through Congress whether that's worth funding. Then we'll know where 99% of the Earth-crossing asteroids capable of causing this kind of global catastrophe are. There are some who advocate the construction of nuclear interceptors to vaporize these things if we do, in fact, detect one of them. I would argue that that's completely premature. Even in the unlikely event that one of these objects is going to hit the Earth in the next century, which is very unlikely, but even if we were to find one that was going to smack us soon, it is overwhelmingly likely that that collision will be hundreds of years in the future. So we'll have a long time to think about it. And knowing that it's going to happen, say, 200 years from now, we'll focus our minds on the problem, and we'll have the technology of 100 years from now to solve the problem. We don't need to be building a fleet of nuclear rockets to do it now. That's the wrong way for us to be spending our money and our scientific expertise. But I think that for a small investment, it would be prudent to catalog where all of these objects are. I'd be happy to take questions, and thank you very much. Yes? Just a moment. I'll take questions for 5 or 10 minutes, and then we'll call it a night.
Why did you say we have 100
The question was, how is it that we know that if we do find an object that's likely to hit the Earth, if we do find an object that's going to hit the Earth, that it's likely to be a few hundred years before it hits us? That's a statistical statement. It's based on how often these Earth crossers how likely these Earth crossers are to hit Earth. It's statistically likely that if you find one whose orbit, when you follow it around enough times, tells you that it will hit the Earth, it's statistically likely that that collision is far in the future. It's not necessarily the case. It's only a statistical statement. You won't really know the answer until you catalog them all. Are there any other questions?
Okay, thank you. And anyone who wants to talk to him, he'll be down here for a little bit, at least, if you've got questions to ask him. Thanks.
Come on, guys, let's really say some shit. What?
Let's go ahead and get our reports to Craig.
It's not such a lot of appreciation of feedbacks. They're there.
That's rough. Yeah, I had to go to